I don't know if we've met. Hi.
Nice to meet you, I'm Kenneth.
Yeah.
Finally, I met you in person. I still haven't.
Oh, yeah.
Yeah, great. I mean, I'm not the same tactic, but
You know.
I think you know much better than me. Okay, but, oh, yeah. Yeah.
Yeah, I think it's like. Just so what is this? What is information? They don't have the different functions. Differential.
Yeah, whatever you think. So where do you work now?
In Hong Kong.
Oh, in Hong Kong.
All these information.
Very natural question. And you can discuss more.
Yeah, we should. You've got some of my like Casale or Ronnie Nagloo. Yeah, you've met. Oh, you haven't met. Or David Blazquez-Sanz, but he's less likely because he's lumber. Which is a little bit.
So it's kind of exponential.
Yeah, and there you
All right, so let's perhaps get started with the last talk for today. We have James Freitag from UIC, who's going to speak on a differential approach to Ax-Schanuel.
Okay, yeah. I think it won't be too technical because try to make some general points and also some connections to dynamics, algebraic dynamics. Although I think some of the people doing algebraic dynamics weren't able to arrive. So, okay, so there will be three parts, and so start with how I started thinking about these problems. Because I'm mostly a model theorist, but Jonathan gave the Tarski lectures in Berkeley in 2013. I think it was from then that Tom Scanlon and I started thinking about this kind of general problem. I think Jonathan mostly talked about his paper, took a picture of there. So the general kind of form of the problem is that you have some algebraic varieties or maybe open subsets of such, and in an analytic map, which isn't algebraic. And maybe the primary case considered in this paper, or primary from my perspective at least back then, was that you take I don't know why I've written it this way, I just mean the J function on each coordinate of the upper half plane, on each copy. But I should have maybe just written J bar or just J. And you try to characterize which algebraic varieties on the left get mapped to algebraic varieties on the right, or open subsets there. Okay, and yeah, I mean, there are other cases of this considered in that paper, maybe with also the Weierstrass P functions and exponentials or something like that. Okay, at first, pretty much, maybe there were a few minor things that we were able to notice. We were pretty much just using Jonathan and then later other people's work on this kind of problem to prove things about differential equations that we wanted to know. So I think at the beginning, most of the knowledge transfer was going only in one direction at all. But it was interesting because there were some old, I guess old means from the 90s or something, open questions about differential equations that you could answer in this way. And there's one example. There was a question of Rashofsky. Yeah, I don't expect maybe that the language makes sense to everyone, but just to say that there were interesting outputs, even from mostly just knowing, mostly just using Jonathan's result. Yeah, and maybe there were a few interesting outputs, like Tom and I proved some very bad bounds for intersections of non-bialgebraic subvarieties with isogeny classes. And then I think later Gal improved those quite a lot. So there were other things. Okay, but the connection to differential equations comes because the J function satisfies this third order differential equations, nonlinear. This is the Schwarzian derivative, and it's maybe not so surprising to see it because the J function is invariant by PSL2 of Z, and the Schwarzian exactly eliminates the quotient of two functions being related by a linear fractional transformation. So, okay, so there it is. And the way that we were thinking about okay, so here's like maybe I guess the simplest case of the bialgebricity problem is you have to ask which algebraic curves. I guess it only really makes sense to ask about algebraic curves which intersect H2, intersect the upper half plane. Which algebraic curves have the property that when you take their image, it's algebraic. Okay. And we were thinking along the lines, maybe from the same problem, but just from a different point of view. If you take the generic point of a curve, and then think about the differential equation, d by dt1, then these functions here satisfy some. Well, the first one just satisfies the differential equation of the J function. The second one, it depends a little bit on the equation that T2 satisfies relative to T1, but not so much that it's unpredictable, because you can play around with the chain rule for the Schwarzian and see what equation it satisfies. And so the idea is that if you could just understand the differential equations that these two functions satisfy in some fairly complete way, then you would be able to understand what are the possible bialgebraic subvarieties for those functions. And so that's kind of the whole idea. It's a fairly simple idea. The problems are basically the same. Okay, and so, okay, at first, as I said, I think the transfer was only one way. We're seeing, you can see something interesting about these differential equations from what people were proving, but often, the assumptions on the functions that would appear, would have something to do with arithmetic or some particular number theoretic situation. And I guess our idea was that somehow only the shape of the differential equation should be somehow, whatever that means, should be enough so that you could prove something strong enough to answer these questions. Okay, so that's what we started doing. And I guess in the first case, we started thinking of other discrete subgroups of SL2. So, and we were trying, for various reasons, we were trying to work out the general case of a genus zero Fuchsian group of the first kind. explain a little what it is. I expect some people probably know. It's a discrete finitely generated group. And of course, just like SL2 of Z, it acts on the upper half plane in the standard way. By discrete, we just mean there's no limit points in H, and by first kind, we mean that every point in the boundary is a limit. Okay, and genus zero means that the quotient of H by gamma is a genus zero algebraic curve. It turned out that that's not ultimately necessary, but at first it was. So yeah, here's an example. Triangle groups give many examples that are easy to write down. Here we wrote them down. And there's a picture sort of the this reflection group where each of those pieces of fundamental domain. But the existing results really wouldn't work to prove anything about this, as far as I know, because most triangle groups aren't arithmetic, and as I'll explain, they're the solution sets of their differential equations, when you're arithmetic versus not, behave in a much different way. Okay, so, but again, these, for any gamma, any group, as in the previous several slides, you'll satisfy an equation of the same shape. This Schwarzian equation with this this rational function. And basically our idea was that things probably depend in some way on this rational function to prove something strong. But there should be something that we can notice about the shape of that rational function that lets you prove a similar complete characterization of the bialgebraic subvarieties. In the case that the equation comes from a group gamma, that's true. And in the general case, we're still working on that problem. So we don't know exactly. Yeah.
Just to make sure I understand this,
Yeah.
you want to understand bialgebraic subvarieties from a product of copies of the upper half plane mapping to a product of copies of the quotient curve?
Yeah, that's right. Yeah, thanks. Yeah, sorry if I didn't make that clear. Yeah, that's exactly right. That was the goal initially. Yeah. And ultimately we did, at least in the case that that rational function comes from a group, comes from one of these genus zero Fuchsian groups. I guess we didn't put of the first kind, but okay. The title was already fairly long. And I think as far as I know, for this particular kind of result, I think that the proof in our paper is the only one I know exactly that covers all of those cases. But just like in the case of SL2Z, the uniformizing function, when you restrict to a fundamental domain, is definable in a no-minimal structure. That's no problem. That's all the same. But I don't know any proof that uses. I don't think there's any proof that uses O-minimality, but and the characterization is just as clean. For those who know the original characterization, I guess I'll say it more later, but all of the bialgebraic subvarieties come from two coordinates satisfying, say in the domain, satisfying a relation with the commensurator, being related by an element of the commensurator of the group.
Commensurate?
Yeah.
Can you repeat the word?
Yeah, commensurator. Yeah.
Can you say that? I'm sorry, I apologize.
So right.
It's like commensurable.
Yeah.
Commensurator.
Yeah.
Makes it active, okay.
Yeah, it makes it more commensurable.
Yeah. Yeah, so,
Okay.
okay,
But maybe, yeah,
I could say more about it, but, okay, I mean, yeah, I just mean two groups are commensurable if their
Okay.
intersection's finite index in both. And,
yeah.
yeah, and,
Is that I know.
and then the
yeah.
commensurator, by that I mean if you conjugate by that element and then intersect the conjugate of your group with the original group, that they're commensurable.
Okay,
So-
okay, I understand, yeah.
Yeah.
And then you said this is in relation with, because I have difficulties on
Oh,
the
yeah,
semantics.
yeah, and so like in the case. So it should be that, so let me just take the simplest case. Okay, let's say that everything's genus 0. Then the subvarieties which are special here are those where the two coordinates are related, and this is an element of the commensurator. Okay. Yeah, so just
Thank you very much.
yeah, no
Thank
problem.
you.
Yeah, so
But
Yeah.
by the way, I think my paper with Emmanuel Ulmo does also some sort of.
oh, okay, yeah, that might be very possible. Yeah.
For triangle groups, not for other.
For triangle.
That's
groups.
for triangle.
Okay, all right, yeah, so, yeah, that's certainly possible. There's been a lot of results in this area in the last decade, so a lot of great results. So, okay, so, okay. This result's been generalized in a number of ways, and I'll say something about the generalizations, but and then also I'm going to try to say something about well, something that I mean maybe only I regard as a generalization, but I'll try to explain that perspective. Okay, so I guess the next probably easiest result to talk about is a few years later, a stronger result was proved, by Pila and Zimmerman. Maybe this is about 2015 or something. And you assume, okay, yeah, if the two coordinates satisfy a relation like this for the J function, then that's exactly when the images lie on a modular curve. Okay. So I've, for some reason, chosen to say this. Phi n is a modular polynomial. So for some reason, I've chosen to say this about the image and not the domain, but okay. So Pila and Zimmerman proved this stronger result, which says that if you look at this situation and you consider the transcendence degree of each of the coordinates and their first and second derivatives, okay, I'm simplifying things a little bit, they prove something stronger than this. In fact, then as long as you don't lie on a modular curve, you see, if you lie on one of these modular curves, the transcendence degree will drop by a lot because you'll be dropping the transcendence degree here in the domain and for the derivatives in the image. But if that doesn't happen, then you can't drop the transcendence degree by much. Okay, and I put +1 here just to make it simpler. I mean, they actually prove something. They prove something having to do with the rank of the matrix of the derivatives of the ZIs with respect to each other. Okay, yeah, and then I guess I'm just stating the sort of geometric way in which you could describe this, where, yeah, maybe all this notation's not known to most people. By this I mean something. This is sort of this is the second jet space, the variety which parameterizes the J function and its first and second derivatives in this situation. So it just says somehow if you have an algebraic variety in this product and it intersects the graph of the J function on each coordinate in such a way that the Zariski closure of that intersection is small, then something very, very special has had to have happened, and you have to lie on a modular curve. Okay, and I guess that's exactly what I say in the third point there. Okay, yeah, and yeah, there were many analogous results, generalizations, and other nice things proved in higher dimensions, and for more general situations by numerous people, because these kinds of results are part of some of the essential ingredients in studying some Diophantine conjectures and theorems. Okay, so then I'll say in the context of arbitrary groups, gamma here, these arbitrary Fuchsian groups that you might take. Oh, and I guess there was too many names here. So this is David Blazquez-Sanz, Guy Casale, me, and Ronnie Nagloo. So we stated in terms of sort of germs of power series and multiple variables. And I guess in the statement here, I'm using this term geodesically independent, but that just means that that the variable, this germ here, is not a constant. It's not just a complex number, and there are also no relations of the form Ti equals gamma of Tj for one of these things in the commensurator. Okay, so assuming that, then the transcendence degree of this collection of power series, it can't be too small. It has to be at least 3n plus the rank. This is the rank of the matrix of those derivatives. Okay, and I guess this is really completely analogous to if I had stated the theorem of Pila and Zimmerman precisely, they prove something exactly like this in that case, in the case of SL2Z and the J function. Okay, so just some comments on this that are interesting things to observe, I think. So the algebraic relations for the solutions of this is some big system of differential equations. They all come from algebraic relations between pairs. Yeah, and then I think I mentioned before, we proved actually we're trying to work on this in kind of generality, just based on the shape of the equation. But you need some assumption. We have examples that show you need some assumption. Okay, we don't know exactly what that is yet. That's still in progress. But in the case that the rational function comes from a group, we have a complete characterization. Okay.
Can I ask
Yes.
a question for people who are not in the topic?
Yeah.
So, how does it behave when I replace the coordinates by other ones? I multiply them by unit, but not constant units. The assumptions are changed. I mean.
Yeah. So I mean, so if two coordinates like you mean like T1 and T2?
Yes, for example.
Yeah, if T1 and T2 satisfied some algebraic relation, then their derivatives would satisfy a linear relation, right?
No, that I understand, but if I replace the Ti individually by units times Ti's, units in S.
Oh.
1 plus A1 S, etc. How does that?
So I mean, well, okay. I guess that's a special case of the rank of.
The rank won't change.
Well, yeah, the rank won't change, but I mean.
That's why I asked.
But neither will the transcendence degree, I think, of the there. So Yeah, it's a good question. I see. Sorry, at first I thought what you were asking is if T2 is equal to T1 times a unit or something.
I understand.
Yeah, okay. Right.
Is there a version that handles different groups simultaneously, like gamma one, gamma two?
Yes, yeah, that can be done. The statement has to be a little more complicated. Yeah, but okay, there is some way to handle different groups at the same time, which I'm not going to attempt to state right now. Okay, it's also true that this wasn't sort of the main thing we were doing. We were trying to give some higher dimensional version of this, but I think so to state it requires a fair amount of machinery, which I'm not going to try to state in all precise terms, but the higher dimensional version of this has to do with, you set up with for some algebraic group, a G principal bundle and a flat connection, and you make some assumption on the differential Galois group of the connection, and you have to have some assumption. That kind of assumption for us sort of plays the role of the shape of the equation being in the right configuration so that we can do the kind of Galois theory to prove something. And so let me just say, like in the higher order settings, it's still true that the algebraic relations between solutions have this very strong rigidity property where they're all essentially binary and over the field of definition. Okay, all right, so now I want to talk about a weaker result, but a more general class of equations. In fact, any equation.
Can I ask something to you about?
Yeah.
When you were talking about generalizing to a more to a R of Y that's a group, you're still working with this shape like Schwartzian plus Y prime.
Yeah.
And then when you find a solution to this differential equation to replace the J function.
Yeah. So the solutions. It's still true that it may be that the solutions of a differential equation, you just pick some random rational function there. They don't have anything to do with the uniformizing function of the fundamental domain of a group that acts on the upper half plane. But it's still a uniformizing function of some region in the upper half plane. You can prove something like this. And it just might not be the fundamental domain of a group. And so it might be much harder to give an exact characterization of the relations. And so for instance, we've done it just in cases where you assume something really strong about the poles of the rational function, things like that. So I don't have anything to say in general because I don't know the answer. Okay, certainly you have to assume that if you take a Riccati equation with that same rational function, you need to know that Riccati equation doesn't have any algebraic solutions, or else you'll not be able to do it, I think, from our perspective. Okay, so if you weren't sort of involved in this kind of setup with Ax-Schanuel and weakly special subvarieties, bialgebraic subvarieties, and so sort of felt lost. You won't feel lost at this part. I think anybody can understand what I'm going to say next. Just take an arbitrary differential equation, and there's no need to make it in one variable or something or a certain order. It's just I'm just doing this to make the statement simple. So you take some differential equation in one variable, order n. It's nonlinear if these things are going to be non-trivial statements. But you won't lose anything at all if you just assume that the polynomial has coefficients in C of t, and the derivation is d by dt, and the solutions I'm considering are meromorphic functions. In fact, there's a theorem that says you can sort of reduce to that case, maybe not this case, but you won't lose anything just by thinking about this case for the polynomial. Okay, so then just consider the following condition, which might hold or might not hold of the solutions. It could be true or it could not be true. We'll talk about that. So I call the condition CM. It says, pick any m distinct solutions of your equation, this equation up here, and then ask yourself whether those solutions and their first n-1 derivatives are algebraically independent over your field K. Okay, you wouldn't take more derivatives because, I mean, you'd run into the polynomial, so no need to do that. And like I say, this could be true or it could not be true. I mean, they may be algebraically independent or they may not be. In the case of these equations we studied here, they're not. Already you can see that C2 fails, and not just that C2 fails, C2 essentially controls everything. Every relation comes from, is built very rigidly from a C2 relation, yeah.
That's supposed to be like evoking of CM points or differential equations.
I don't know, it wasn't, but maybe that's a good maneuver to suggest. Okay. So let me give some examples to see that this is a non-trivial problem because, you know, for these ones, it's not so interesting. Okay, so again, that's just the condition in case there's, you know, you need to see it again. And you can see that as the numbers go up, the conditions become stronger, okay? Okay, and the condition can just hold for all n for certain equations. That's many such examples. So this is the second Pain-Levé equation with a parameter pi, I mean like pi, like 3.1, yeah, the number. But it doesn't matter as long as it's just like a transcendental, you know, this is fine. I just needed something. Okay, you know, so Cn holds for all n. There's no algebraic relations between solutions of the second Pain-Levé equation over C of t. Okay, and well, I mean, you know, Jonathan showed that the negation of C2 holds for the J function, but like in a super strong way. Every algebraic relation comes from C2 fame. Okay, and okay, if you take a Fuchsian group, there are many Fuchsian groups where, oh, sorry, there's a parenthesis issue, but there are many Fuchsian groups where the commensurator is equal to the group itself. Such things are, you know, like say, for instance, there's many maximal triangle groups. Some people call those maximal triangle groups. The equation satisfies Cn for all n. So, okay, so there's kind of, the question is, can you say something in general? Like just completely general? Could you say anything at all interesting about this? I mean, the examples suggest either Cn holds for all n, or there's a small value of n for which Cn fails. And yeah, and so I guess I'm kind of thinking of this as
Small means what?
well, I'll explain that. So far, small is 2, but that's too much to hope for.
Otherwise, the sentence is maybe tautology, right?
Yeah, maybe, but it's not. Okay, yeah, you can build many examples of equations where C2 holds, but C3 fails. I won't give one of those because I'll just go ahead and give you an example where C3 holds, but C4 fails, okay? And it's easy to do so. If you take a Riccati equation that happens, and you have to pick, I mean, this won't be true for any rational functions A, B, and C, but for most, I mean, you just choose randomly, that Riccati equation is bound to have differential Galois group PGL2, and then it won't have any rational solutions. And I mean, you know, after a linear change of variables, you can write it like this. And it's true that any 3 solutions are algebraically independent over C of t for an equation like that. It's assuming that you don't have any any algebraic solutions to the equation. These are all transcendental functions, but they're also all independent. But if you pick a fourth solution, any fourth solution that you want, you can always write it in terms of the first three solutions and some constant, some complex number. So somehow C3 holds, but C4 fails even in a really strong way.
Is this structure that the particular solutions you pick don't matter? Is that?
The solutions you pick don't matter in this case. Yeah.
Just in this case or in general, or?
Well, in the way I formulated the problem, it's kind of it's a statement about, for any n distinct solutions. So by the formulation of the problem, it doesn't matter. But for particular equations, maybe if you said, maybe you would want to insist that the solutions be generic or in some sense, and then maybe it can matter. Yeah. It's a good question. Okay. All right. So this is kind of bad news because, I don't know how much the examples suggest this last thing anymore, because that was an order 1 equation and already we're up to 4. So maybe, I don't know, things seem a little weird. Okay, but actually, this wasn't at all how Reshofsky phrased things, but a result of Reshofsky implies that for order 1 equations, C4 actually implies Cn for all n. So if you have C4, then you have Cn for all n for order 1 equations. It's not obvious, but you can deduce that. And so the question really then that we're asking is, can you prove a higher order version of Reshofsky's result? And that's what Rahim Musa and I set out to do, especially after we saw that so many of these nonlinear examples have this property where all of the algebraic relations were controlled in this fundamental way by C2 relations. I think we would have never tried it if not for that, okay? Yeah, and surprisingly, you can prove something better than Reshofsky for higher order equations. But first I have to tell you what minimality or strong minimality means for a differential equation. It's actually a classical notion. It was considered, even in the 19th century, it's much different language by people like Painlevé. So this is just my same setup as before. And we say that one of these differential equations is minimal, or model theorists might say strongly minimal, if whenever you have a solution over any differential field extending the field over which the equation is defined, it's true that the transcendence degree of a solution and its derivatives, it's either 0, like the solution is algebraic over the field K, or maybe just in the field K, or n. It's either generic or it becomes algebraic. And you might think, this is some really special property, but in fact, if you just write down a random nonlinear equation, like with 100% chance that satisfies this, there's like a theorem of Remy-Jowy to that effect, and one of myself as well. Okay, so for minimal equations of order larger than 1, it's okay, there's a proof, but and I'll kind of even explain it in a second. There's a proof that C3 implies Cn for all n. And this notion that Rahim and I introduced, called the degree of non-minimality of a differential equation, well, it turns out that in this field, sorry, the typesetting is a little weird. This is the field big K. It turns out that you don't need to study arbitrary fields of functions for this big K. It's sufficient to study a field of functions generated by solutions to your original equation. If this condition fails, then already it would fail in such a field. The degree of non-minimality is the number of generic solutions of your equation that you need in order to see that this condition fails, if it ever fails. Okay? I realize that's kind of a complicated thing to parse. Okay, so how then did we solve the general problem? Because it's not true that every equation is strongly minimal. Okay, Well, Raheem and I, we designed this, well, I mean, coming from model theory, some kind of theory of vibrations that let you reduce to equations that are very close to being minimal, not exactly minimal, okay? But you could see that relative to our theory, you just had to handle these three distinct cases. And several of them were very easy to hold, to see, sorry, I don't know why. I mean bi-algebraic or whatever there, but in the first case, C2 fails, and the algebraic relations are completely rigid, as in the case of Shimura varieties or any of these cases I mentioned before. In the second case, somehow your equation fundamentally has to do with the torsion points of an abelian variety. And in this case, it has to do with some equation that we call a Manin kernel. In this case, or a torsor of such, in this case, you'll have a failure of C3. And then in the last case, it's the hardest to deal with. It's what model theorists call being internal to the constants. And this was classically considered in differential Galois theory by Kolchin and many others. It's what Kolchin calls being strongly normal. So in this case, we really had no idea what the bound would be, or even if there would be a bound. But we know something very powerful, and that's that there's a differential Galois group acting on the solution space. And the differential Galois group is actually isomorphic to the C points of an algebraic group acting regularly on an algebraic variety. The only real complication is that it's only isomorphic after you do a big base change. You need to extend the differential field to realize that isomorphism. If we could control that base change, then all the theorems would be very easy to prove, but we still don't know how to do that exactly. I mean, in the case of linear equations, it's simple to describe what I mean. You just need a fundamental set of solutions to your linear equation to realize this isomorphism, to realize that the differential Galois group is isomorphic to a matrix group. Okay, but we're in a nonlinear settings. Things are more complicated. I can't say exactly. So the idea is to reduce the problem to purely group theoretic information. And if you could do that, you only care about the sort of abstract isomorphism of groups. You don't need to use that it's actually definable over some particular field. Okay, and the thing which proved crucial to understanding this was a notion of higher transitivity that people had studied called generic transitivity. I'll define. Yeah, sorry.
I'm a bit lost.
Yeah.
What is X before we hit it?
Oh, it's like the solutions of the differential equation. Sorry, I didn't say that. The solution set of the differential equation.
Can you say what it is if I have a nonlinear ODE like we had on the previous slide?
Yeah. It's just, I mean, it's just the collection of meromorphic functions satisfying that equation. Yeah. Maybe or maybe the germs of such if you need to work closely. Okay, so so this first definition I expect many people know. It's just a general definition about groups. So you say a group acts k transitively on a set if you can map any two distinct tuples, k tuples, to each other. That notion plays a big role later, but the thing which we had to study first was a weaker notion that's called generic k transitivity. So if you have an algebraic group acting regularly on an algebraic variety, we say it's generically k transitive if when you act on x to the k, there's a Zariski open orbit. So there's a dense orbit. Maybe you have some smaller dimensional orbits, who knows? But there's this big open orbit in x, well, here x to the 2, because that's the limit of my drawing. Okay, so it turns out that, just some, I mean, maybe we all know many examples of generically transitive group actions, like the big orbit is the set of bases in a vector space action of GLN, and it's the set of projective bases in the action of PGLN on projective n-1 space. Okay, so there was a conjecture of Borovic and Churlin, and made in a much more general context. We haven't resolved the conjecture in general. It's made in this context of groups of finite Morley rank. If you don't know what that is, don't worry about it, but it includes the setting of algebraic groups. And the reason that Reshofsky had been able, well, I mean, he didn't say this, but the reason his theorem shows that, C4 implies Cn for an order 1 ODE is that he proved the Borovic-Churlin conjecture when the dimension of X is 1. Okay. So the problem's now, it's a big problem for people doing groups of finite Morley rank, and Rahim and I proved it for algebraic groups of characteristic 0 over an algebraically closed field. We also know something about other fields, but maybe you have to be much more careful. That could be very complicated if you're not working over an algebraically closed field. Also, at least the proof that we wrote down does not work in characteristic P, because we use some things about, I don't know, we don't know that much about Lie algebras, but we use many facts. We weren't working in characteristic P. So, probably someone could try it. And if you know enough about algebraic groups in characteristic P, maybe you can do it. It's also true, you can just try to solve this problem for O minimal group actions where, you have an O minimally definable group G acting on a definable set X. Ask when there's a dense orbit in X to the N. Or ask when there's an open orbit in X to the N. There's variations there. There is a bound that depends only on the dimension of X. It's due to McPherson and Tent and Moseley, but it's probably not an optimal bound because they were solving a different problem. But it follows from this paper of McPherson, Moseley, and Tent, and from the late 90s, I think.
So this is a purely algebraic statement. Yeah, you don't need to, like the thing you guys proved. Is there any hidden differential equation somewhere?
No. This is a purely algebraic statement, purely a statement about algebraic groups. Yeah. And you see, I guess the reason why people who studied algebraic groups had proved things kind of like this, but the statement is really about the set X and then the possible actions on the set X. And most of the analogous theorems for algebraic groups are about the group G and its action on the left cosets of an algebraic subgroup. Because if you have a transitive action of an algebraic group on an algebraic variety, it's definably it's isomorphic to the action on the left cosets of the stabilizer of any points in it. So you may as well reduce that case, and that's what they did. And they're more fixated, say, on an algebraic group. So it's sort of like an orthogonal question to most of the questions you might ask there. Okay. Yeah. Okay. Yeah. So it's purely, yeah. Okay. Now it turns out if you play with the difference between generic transitivity and outright n-transitivity, that's essentially how our proof goes. Rahim and I proved that when the order of the differential equation is bigger than 1, then C3 implies Cn for all n. Really surprising. We didn't think that would be true. And the reason at the heart of it, why that's true, is that there's just not very many two-transitive algebraic group actions. So they were, in fact, entirely classified by a group theorist, Knopp. They all have to do with something like PGLN acting on projective n space. or certain subgroups of the group of affine transformations. I mean, like a subgroup of GLN semi-direct product with the vector space, acting regularly on the vector space. Okay, so it turns out that the key thing to notice is just some group theoretic fact about orbits. You know, all the two transitive Galois group actions have this infinite but non-generic orbit in x to the third, where x is this algebraic variety, and that orbit gives you an algebraic relation of the corresponding differential equation and its solutions. Okay, and then like a week after we proved this, Remy Jowie, who became our co-author, emailed us and said, I think you could prove an even better theorem. We said, I don't think so, because I mean, 3. And he said, well, when the equation has constant coefficients, we should think more, because all of the groups in your list are centerless. And we should be able to prove that the differential Galois group is never centerless for autonomous equations. And that's what we did. And so for equations with constant coefficients, C2 implies Cn for all n. And now it doesn't seem that much different from this situation. You know, we don't have the same exact kind of rigidity. It's not where I'm not saying that every algebraic relation is controlled by a C2 relation. But if there's a non-trivial algebraic relation, then already there has to be a failure of C2. So I think it's the best you could hope for, probably. Okay, so let me finish in the last bit just by saying there's an analogy which I think hasn't been considered much, except by me, between difference equations or algebraic dynamical systems, bi-algebraic subvarieties, and then so here we're sort of on the differential side of things, thinking about these. And then what should be the analog for a dynamical system? I think you should think about invariant subvarieties, I'll say what it is, or periodic subvarieties. And so maybe there's a lot left to say there. So I'll think about an autonomous difference equation. So difference equation, for me, I'm thinking about difference equations only over fields. So, you know, say sigma is an automorphism of a field, and then I'm considering algebraic difference equations of the form, you know, a polynomial relation in the variables and their sigma translates. Okay, so just the exact analog of a differential equation, but an algebraic differential equation, but for a field with an automorphism. And if the automorphism is trivial on your base field, then this is exactly just, it's literally the same thing as considering a rational map, rational self-map of an algebraic variety over C. And the corresponding difference equation is just obtained by looking in this, some big difference field containing the complex numbers and saying, where is sigma of y equal to phi of y? Okay, that's what I mean there. And so what exactly this difference field here is more complicated than in the differential case. Remember, I told you, just think of C of t, and then the solutions are meromorphic. You can't quite do that here. It'll be more complicated. But
what was sigma? Sorry.
It's just an automorphism of the big field K.
Okay.
Yeah. So, and so in this case, I'll say that a subvariety is invariant just if the rational map, the subvariety shouldn't be in the indeterminacy locus of phi, or you should just assume phi is regular or something. But phi of W equals W, I just mean it's dense, W maybe even. The analog for, what I defined as minimal or strongly minimal is that it just basically says that there's no invariant subvarieties in V. Okay, the picture is more complicated when you don't assume that the coefficients are fixed by sigma. Okay, that's not maybe so surprising. In this case, we call such a system a sigma variety. These were, like, for instance, intensively studied by Pink and Roessler and various other people in conjunction with certain number theoretic conjectures. When I have a non-trivial automorphism of the field over which I'm working, by V sigma, I just mean, if you work with equations, you just hit the coefficients of your defining equations with the automorphism and cut out the resulting variety. That's what I call V sigma. Okay, and again, you can define what it means to be invariant. It just means that phi of W equals W sigma, or it's dense in W sigma maybe. And again, the non-existence of some positive dimensional irreducible invariant subvariety is what we mean by minimal. But you always have to think about extensions, unfortunately. Okay, so and the point is that invariant subvarieties exactly capture what it means to have an algebraic relation between two solutions of your difference equation, in the same way that bialgebraic subvarieties do for differential equations. Okay, like here's a particular way in which you could have lots of invariant subvarieties. Pretend that sigma is trivial here, and so you have a map you have a diagram like this that commutes. We call such an F an invariant rational function of the system. Then all the fibers of that function will be some hypersurfaces in X, which are invariant. Okay, if this map down here is the identity. Okay, it could be very complicated. I mean, okay, I probably looked up this example at some point in the past. I don't know how to see it now. But this is an invariant rational function of this system. Okay, and you can see that this really depends on possibly base change or looking at products, because there's no invariant rational function of X goes to X plus 1. But if you consider the system product with itself, well, then like X minus Y will be an invariant rational function, for instance. Okay. All right. So, okay, yeah, let me just say, I think I'm running out of time severely. So the existence of an invariant rational function has something closely to do with Zhang's Zariski dense forward orbit conjecture, but I won't say what that is right now. And so it's well understood when you get an invariant subvariety arising from the existence of an invariant rational function. And the question I'm trying to answer is, and the unfortunate thing is that you can't control the base change very well. You may get an invariant rational function only in some high dimensional product of your dynamical system with itself. The product depends on the number of copies of X you have to take depends on the dimension of X. And this bound, maybe it's not known to be tight in this paper, but we know that it's tight. Okay, so yeah, and so the question is, if you have interesting invariant subvarieties at some point, can you just bound the product by which they appear? Analogous to the differential equations context. If you have non-trivial algebraic relations between solutions of your differential equation, do you have non-trivial algebraic relations between 4 solutions or something like that? Okay, and the answer is yes. Okay, there's a complication because I have to say what I mean by invariant. Like I don't want to take a fixed point of one of the maps and then take the product of the fixed point with the whole system. That's not interesting. I mean an invariant subvariety that projects dominantly onto each copy. Okay, so that's what's on this slide, but I think I'm really out of time. So let me just say what we can prove. So if you have some non-trivial invariant subvariety appearing in some power of your sigma variety, then already there's one in the 4th power. And this bound is tight. You can't improve it in general. Maybe you could improve it in some cases. And it's equivalent, completely equivalent, kind of by the perspective I was explaining. to saying that if you just take some rational difference equation, so one of this form here, and there are some number of solutions so that those elements are algebraically dependent, then already there are 4 distinct solutions that are algebraically dependent, surprisingly. Okay, yeah, and this only is non-trivial in the non-autonomous case. You can prove something in the autonomous case, but you can prove something much stronger. Okay, so let me just say something about the element of the proof, because I think it's pretty interesting. Okay, so there's kind of a fibrations argument that we do, analogous to the differential case, but where most of the work was already done by Chatsidakis and Rashofsky. And then you get to a point where you need to understand a certain automorphism group. And unfortunately, the automorphism group is not an algebraic group acting on an algebraic variety over an algebraically closed field. That would be great if it was, but it isn't. It's almost that, except you have to replace everywhere algebraic with definable and algebraically closed with pseudo-finite characteristic 0. And so sorry, I can't say what exactly pseudo-finite is right now. It means that you're elementarily equivalent to an ultra product of finite fields. Okay, and so, you can use the Borvik-Churlin conjecture, but pseudo-finite fields are not algebraically closed. You sort of need to know that the orbit you're trying to apply it to is absolutely irreducible. And unfortunately, because like point stabilizer orbits are bound to become and are bound to become reducible at some point in these higher group actions, I don't really see how to do that. But fortunately, there's like a big hammer that you can use if you choose to get it out. Because this field C is pseudo-finite, it's true that the group theorists just classified all the 3 transitive finite groups. They just made a list. And you know that what you are getting is an ultra product of these things. And if you think about it carefully enough, you can rule out many of them. So all of these groups up here are just finite. And the solution set to our difference equation, our variety, is not finite. So we're not going to be able to get ultra filter many of these in our ultra product. If you take an ultra product of Sn or An for where n is unbounded, it definitely can't appear as a difference Galois group. You need to prove that. And the same for this group of affine transformations over a higher and higher dimensional space, but in characteristic 2. Okay, those can't appear. And the key thing is really, you can prove much more, but the key thing is that the group actions appearing here are just not 4 transitive. They're 3 transitive, but they're not 4 transitive. And okay, yeah, so that was the sketch of the argument there. And that lack of 4 transitivity is exactly what makes C4 control everything in the case of difference equations. Like I said, it can't be improved because we do have many 3 transitive group actions. And then I'll just say, you may want to try to duplicate what Rahim and I did for different differential equations. I did. But it's a lot harder because if you look at the list of 2 transitive finite group actions, like I could put the 3 transitive ones on 1 page, but the 2 transitive ones take like several pages of the book. And so you need to do a lot more work. But okay, Remy Jowie and Ula Karamuki and Nick Ramsey and I are working on that now. I think that we more or less have proved it, but say that's in progress. Okay, so how do I expect one to use this? Well, for most such systems, we don't expect there to be interesting, irreducible invariant subvarieties. But it might be hard to prove there aren't because of this base change issue. And we expect that, that you try to prove that there aren't any interesting, irreducible invariant subvarieties by bounding this degree of non-minimality. Okay, and then I'll just say, this technique, but like in really restricted settings, has been used really profitably by people like Like this essentially this kind of reasoning powers the proof of Medvedev and Scanlon of the Zariski dense forward orbit conjecture for products of curves. And there's some elements of this in the proof for maps of surfaces as well, but the general conjecture is widely open. Okay, and then I'll just finish by saying, okay, ominimality has been, probably the biggest tool for proving things about bialgebraic subvarieties of differential equations, even if it's not directly arguing about like the differential equation, even if you're thinking about it in terms of analytic functions. And so what about the case of algebraic dynamics? Okay, thanks.
Questions for James?
Can you give us a hint in the case of differential equations, like how transitive actions of like generic transitive actions of a group show up?
Yeah. I mean, so the thing is that so as soon as you get a failure of okay, you're going through and you're saying, okay, I have to understand this base change where I'm adjoining to my field generic solutions of my equation. As soon as the Galois group fails to act generically transitively, then you just know that the very next solution that you pick will be on some lower dimensional orbit in the product space. And that lower dimensional orbit, okay, you need to argue this bit. It will correspond to, I mean, it's the orbit of an algebraic group, and so it will lead to an algebraic relation. Yeah, you can argue that. Yeah, that's the whole idea. It's a very like simple-minded idea. You have to prove something completely general to use it. Yes. Yeah.
Yeah, so from this differential viewpoint, I mean, I was wondering whether you can reprove for a Fuchsian group, whether you can reprove the Margulis commensurability criterion for arithmeticity. Whether from this viewpoint you see whether there are many or few bialgebraic varieties that are not horizontal or vertical. If you detect this.
Yeah. I mean, exactly what we proved is that the you'll only have finitely, for instance, you'll only have finitely many weakly special subvarieties that, as you say, aren't horizontal or vertical, exactly when the index of the group gamma in its commensurator is finite.
Yeah, that's right. But I mean, in doing so, you reprove the commensurability criterion, or you're using it to get this result? I mean, like,
you mean like the characterization of such a group is arithmetic?
Even
no, we're using
finite.
Yeah,
that's kind of an input. That's
yeah. I mean,
could you reprove it from this viewpoint? I mean,
I don't know. I mean, like, it depends how you state the theorem. I mean, like, just to state our theorem, I mean, you don't need to use that, but to know that the collection of groups gamma, so that there are algebraic relations of unbounded degree are exactly the arithmetic groups. We couldn't prove that. We would use, to know that collection of groups is arithmetic. Yeah, that's like an input for us. I don't know, maybe you could prove it, maybe not me.
I'm just wondering, your proof of the n+2 transitivity bound for generic transitivity.
Yeah.
Is that just a brief hint about the proof? Is it algebra geometric, or is it more let's look at all groups and understand what they're called?
No, it's like let's look at all groups and try to reduce to some extremal cases. And like the extremal case is where the extremal case that ends up making the bound tight is exactly when the point stabilizer is a maximal parabolic subgroup, and then you have to compare the dimension of a maximal parabolic subgroup to the dimension of an algebraic group, and then you do some playing around to try to reduce to the case where the algebraic group is simple, And then.
Thinking diagrams.
Yeah, and then it's a Dinkin diagram game, and then, there's like, just massive amounts known about that situation. Yeah, so no, actually, I talked about this problem, because, an algebraic geometer in my department has written about generic transitivity. And he suggested some possible paths to like an algebro-geometric proof, as might not surprise you, but I wasn't able to successfully follow his strategy. Maybe someone can, maybe Azet can. Yeah.
And can you prove, just a quick follow-up, can you prove a classification where if you're in the extremal case?
Yeah.
Okay.
Yeah, in the extremal case, the action has to be definably isomorphic to PGL n acting on projective n-1 space. It's the only extremal action. But that really closely depends on the field being algebraically closed. Yeah, and over non-algebraically closed fields, I have no idea.
Ellie?
Yeah, in fact, it was my question. So where does it intervene with the fact that the field is algebraically closed?
Oh, yeah. Well, for me, everywhere, because I really don't know how to prove anything about.
I guess it falls because you can define arithmetic twists of PGLN, right? And this one, and you can get other varieties over lower fields that become isomorphic over Q bar.
Yeah, I think, yeah. So there.
But the dimension doesn't change. I mean, this was what but I don't understand much.
No, but the theorem is still true. It's just a classification failed, right?
No, yeah, I'm talking on the conjecture you put.
Oh. Yeah.
Where you have an open orbit of the maximum dimension.
Yeah.
When the group acts diagonally on x cross x cross x, and you are counting the number of factors, which makes it extremal in that case. And I was wondering, you were saying that.
Yeah. So maybe that would be okay if you
Okay.
formulate the. I see. If you formulate the theorem in sort of the exactly right way, so that it doesn't depend on the field. The way that we wrote it depends on like looking at the points over the complex numbers, but yeah, maybe it likely.
Those points, but your formulation on your slide, which I don't really recall very precisely, but you were talking on opens, that an orbit is open, so it's completely independent.
So maybe the formulation would work over arbitrary fields. It's just not.
But then when you have any field, characteristic zeros, I understand that there is a big difference.
Sure.
Characteristic zero, you go to the algebraic closures and you can do your proof. Can't you descend? If it's open upstairs, it has to be open down.
Probably so. Yeah. That sounds right. I guess. Yeah. As long as you start with. As long as you're starting with as long as you're starting with an algebraic variety X that has a dense set of points in whatever field you're trying. You're not trying to prove it for a field set of points. Okay, yeah, sorry. I'm just used to.
Talking on the action and then variety doesn't need it.
Yeah. Sorry, I'm too used to thinking of the points of X over some field, but yeah, you're just formulating it generally. Yeah, I think probably you could do that.
Yeah, so it's nicer.
Yeah.
I don't want to monopolize. I have a philosophical question. So I have been using years ago a lot this theorem of Hrushevsky, not the one you were mentioning, but he was exactly in the same situation. He had an automorphism of the field. He was over a finite field. And then he was looking at correspondences, and then he proves, which is fantastic, the existence of periodic points.
Yes.
Which is precisely your situation. You have you even have an automorphism for him. It was rational. It doesn't matter. An automorphism,
right? And
then you have the sigma of the field.
Yes.
So what I didn't grasp in your theorems is whether you have an existence theorem that you can say in such and such situation, there are points on the graph. I mean,
Oh.
the sigma of x equals phi of x.
Oh,
Because this
yeah,
is precisely
yes,
what you are
yes,
looking at.
yes,
Yeah.
yeah. So there, yeah, I mean, right. So when it's a little bit tricky, but like, yeah, the work of Reshkovsky or Reshkovsky and Chatsidakis gives you such a criterion. When you have an invariant subvariety, which is absolutely irreducible,
Absolutely.
you can deduce over what they call a model of ACFA, a dense set of solutions to sigma of x equals phi of x. But yeah, but
they construct a field over which
Yes.
you have a period. I mean,
yes, exactly.
periodic
Yeah.
points, but you have a points on the graph of
Correct.
sigma minus. Yeah.
Yes, and so right, and so but the conditions are very carefully calibrated. If the variety is not absolutely irreducible, something like that just can't be true, because, like, for instance, I mean, even very simple examples, like if you just have x squared, and like you're just considering a dynamical system like this, and you look at like two copies and you just say, look where f of x equals f of y. I mean, for some high degree thing, I mean, the only automorphism, the only points you're going to find that are solutions to the corresponding difference equation intersecting that graph are the diagonal, because you're mapping all the points to the diagonal in the image, and so all of the components except for the diagonal x minus y don't have a dense set of points, and then you can construct more elaborate examples where components are permuted, and then the theory of Chatsidakis and Reshkovsky basically replaces sigma by a high enough power of sigma to make periodic become invariant.
Yeah, no, that's how
And they have some criterion like this, but some sort of form of irreducibility or absolute irreducibility is probably required.
But that existed already over.
Oh yeah. This is a big long line of work of Udi and Zoe.
Thank you.
Right, let's thank Jim.
Okay, thanks.
For talking.